equal to the integral over the full space-time of phi di phi because of the equations of motion, right? Because this is it. But integrating by parts, on the other hand, this is equal to the integral of the absolute value of d phi squared. But then this is positive, so this would imply that d phi is 0, and this would imply that phi is equal to 0 if I want my solution to be integrable over the full space. Exactly like in the lecture. If you remember in the lecture, it was exactly the argument. There we had some extra x squared phi squared, and so phi really needed to be 0, but I told you at the time, if m is 0, you argue by continuity. You say that you just show that it's constant, but then you can immediately say the constant needs to be 0. And here it's because we are assuming that this was can I add to a solution some integrable solution, and the answer is no, because the constant is not integrable. Right. So it's unique. I mean, if I have a solution, then that's it. I cannot construct two solutions that because there would be the difference needs to be a constant, and that constant needs to be 0 as I approach the boundary. And so this solution is unique, and now we are going to explore that. Okay. So now we are going to take this spacetime here and spell out explicitly what is the Laplace equation in these coordinates here, where I have some angular part and some cinches and so on. And so it's very easy to see, if you go to radial coordinates, that the Laplace equation gives the following: 1 over sinh of y to the d dy sinh of y to the d dy of phi plus the angular part L squared over sinh square of y times phi equal to 0. Okay? Is it clear? And then this equation behaves approximately as, I mean, he decomposed it in spherical harmonics, but I don't see exactly why I need to do it, but maybe I'll realize I need to do it soon, but for now I'll just ignore it. So I take y to be very large to go to the boundary, and I get the equation that dy e to the d times y from this sinh d dy phi is equal to 0. And that gives me two solutions, two possibilities. Either phi goes like a constant, or phi goes as e to the minus d times y. And so we have two options for, okay, it's better to say the following, to say that phi is a sum of functions phi alpha that does depend on y times spherical harmonics that depend on the angular part. Then the angular part taking here that gives a number. In any case, that's irrelevant when y goes to infinity. And then this is just a function of y, and the equation I write, I can think of it is each spherical harmonic by itself. Just that it's really manifested, just a function this y. And so each mode of my decomposition either decays or goes to a constant. And so you see that, and so if you impose that now your mode goes to some specific profile, then you fix the phi alphas, you fix this decomposition here, then you know what the coefficient of the one is. For each mode, right? It's like going to a CMP and getting the constant, the first mode, the second mode, you match with whatever you want. So that tells you what this asymptotic is. And what about the linear combination between the two modes, the growing mode and the decaying mode? That's uniquely fixed by imposing regularity at y equals 0. Okay? So it's exactly like in Schrödinger equation. So the solution is each solution, like we said, it's a constant that I can say phi alpha. At infinity, it's my phi alpha 0 for my solution that I wanted, plus some constant times the phi alpha decaying. And this precise, what is the precise number here, is fixed by imposing that my solution is regular. I solve my y equation, and if I don't fix the coefficient, it will not be regular. And so in this way, we end up with the solution we want. So given a boundary value, we solve this differential equation, and we get this unique solution. And so, and notice that the solution goes to a constant. This goes to a constant as y goes to infinity. So this is just this phi 0, the value as I go to infinity. It's okay. I don't need it. Really goes to a constant. It doesn't blow up. It's not blowing up times a constant like from the matrix like we had before. It's really going to a constant and doesn't care how I approach infinity. Do I go as y squared, as y cubed, whatever you go to the same constant. Okay, so that's important because it tells us that this phi 0 at the boundary is really a function. It's really a scalar. It doesn't carry any dimension. It doesn't really know about the boundary scaling of the metric. Okay, so it has weight 0. Okay, this is going to. And so now we can propose. We can write down what would be the proposal for these correlation functions in the CFP. And so the proposal is the following. If you want to compute these correlation functions, first, you see that you could extract them from a generating function. You could say, compute instead the expectation value of the exponential of the integral of O at some position x times some source. And let's call that source phi 0 of x. You agree that if you define this quantity, then by taking functional derivative with respect to phi 0 and then putting phi 0 equal to 0, you get correlation functions. Right? But you could even just define this as add phi 0 as a source and compute this object even without phi 0 being infinitesimal. It's a definition. It's a nice quantity in the CFT. It contains this as a particular case, but it's more powerful. So here we have a quantity where if this guy has dimension 0, as in that example there, and if I'm integrating over d-dimensional space, then this needs to be some operator at dimension delta equal to d. Okay, that's fine. That's the only thing this exponent could make sense, and we are going to check this. But the claim is, what would be this object? It's an object where I have my correlation function in my CFT. This phi 0 is a generating function for my correlation function. And the proposal is that this should be equal to the path integral of supergravity, which is integrating over all my fields, including phi and everything else in supergravity, but in particular phi, where the boundary condition is that phi goes to phi 0 as I go to the boundary. So compute your path integral, integrate over all the fields with the boundary condition, and at the boundary you get this phi 0 of x. And the proposal is that this should be how you compute this correlation function. Okay, so let me jump most of this. Okay, so let's do an example. Let's check that this has any chance of working. And let's see how we would reproduce this result for the two-point function of operators. Okay, so let's see if this proposal has any chance of being correct. It has the right symmetries, it's a natural proposal, it maps things at the boundary to a path integral in the bulk. And so we want to do this computation to check this proposal. So now let's quickly do this section 2.4 of Witten, which is called some simple computation or some sample computations. So we suppose that as a toy model we have our action for our field to be just some massless scalar, as we said there. And the space-time that we are going to use, we are integrating over d plus one-dimensional axis, and we use this representation, so-called point-coordinate coordinates, to describe what we are doing. These point-coordinate coordinates. And now, what we want to do is to find an explicit formula for phi, where we know the value at the boundary. And that we do by finding, if you want, a Green's function, by finding a function that is some value at the boundary and then allows me to integrate inwards. So let's try to find solutions of this equation, of the Laplace equation, where I'll try to consider that I put my operator at infinity, which, as we said, is the value of x0 equal to infinity. So let's put my operator there to look for the Green function. So the Green function now, as I go from this point x0 to some point that would be in the boundary or in the bulk. So I take this x0 and I want to consider this Green's function k. It would depend on this position of this location of this point P, which would be x0, the coordinate x0, and the coordinate xi at that point. But there is translation invariance, right? Xi is totally irrelevant. So actually it doesn't depend on xi, it just depends on x0. So it just depends on the height. Infinity is where I put my point, it just depends on where I am. This is a trick, because you see, this is a point at infinity. All points at infinity are the same. Remember, the boundary was just a sphere. So we just pick a very nice one, we'll find the solution, and then we use symmetry to get any other point. It's just that it is a very convenient point, because it only depends on one variable. And so, Laplace equation becomes just dx0 of x0 to the minus d plus 1 dx0 of this propagator k of x0 is equal to 0. And we'll take the solution k to be a constant times x0 to the d. This you can check solves this equation. Right? It's obvious, right? We take the derivative, we get x0 to the d minus 1, it cancels this factor, and then the derivative gives it. And now this factor, you see that it blows up as x0 goes to infinity. So it looks like a propagator. There was another solution which was constant, but we took here the growing solution. And this solution has the chance of being the propagator. Now, is this the propagator or not? It's hard to see because we put the point at infinity. So now that we have a candidate for the propagator, let's make infinity to a finite point. Let's make infinity to, for example, the origin, 0. 0 is a nicer point, it's not. How do we map infinity to 0? What transformation do you know that maps infinity to 0? Stereographic projection, that's a good starting point, yeah. But you want infinity to 0, just in one step. What do you do to take infinity and go to 0? 1 over x. So you do an inversion. So you do the following, you send xi, you invert it, xi goes to xi over x squared. If you do it in vector, that's what it means, right? And you can easily see that under inversions, this metric is invariant. If you do inversions, this factor up here transforms, but x0 transforms as well. I runs from 0 to d. And the transformation is such that everything is invariant. Okay, that's fine. That's a nice transformation. And so under this transformation, our naive propagator now becomes k, which becomes x0 to the d, right? It was just this, over x0 squared plus the vector part squared to the power d. Right? And now the claim is that this should be, I should think of it as a propagator. From now, the point is not at infinity. I flipped it, now it's at 0. And it's propagated now from 0 to some point in the ball. Is it plausible? Let's see. When x0 goes to 0, what happens when x0 goes to 0? This k is 0. Right? K is 0 and x0 equal to 0. Except if x is 0. If x is 0, then actually it blows up. Because we get x0 to the 2d downstairs. So we have a function that is 0 and infinity at one point. So that's what that looks like a delta function. Is it a delta function? Yes, it is, because it has the property that it is infinity and 1. And you can check by integrating. If you integrate k over what? You check that if you integrate k over dx1 dxd, you just rescale the coordinates, and this doesn't depend on x0. And so you just integrate with the test function to see if it's well normalized or not, basically. Right? So it has the properties you want. It is at x0 equals to 0. It is either infinity or 0, like a delta function. And you ask, is it a delta function that takes the point at point 0? And the answer is yes, it is. Okay, so we just constructed a function that is a delta function at the origin. But now, instead of the origin, I can now put it at any point, and I can immediately write down a nice solution. Well, you just do the following. You say, yeah, integrate over all points of the boundary. Let's do integrate the, you say, y, the points of the boundary. And then I propagate x0 to the d over x0 squared plus, now instead of x, I rescale, I do a translation by 1 squared to the d times phi 0. So this function is our phi of x. That goes to the value that we want. That's the, we should be careful. It's our function at x0 and x. And when x0 goes to the boundary, this becomes a delta function. And so our function goes to phi 0 of y as we go to the boundary. And infinity, because we proved it was unique, because if two solutions existed, blah blah blah, etc. Right, so we just constructed a solution and it's the unique solution. And you can check that if you expand it past the boundary, it goes to this constant, and it has a subleading term, which is x0 to the power d, and so on. That was the other solution that we said existed. But this is a solution that's manifestly regular, and it's finite, so this is our solution. And now, you see that, so here is the solution. That is defined to go to phi 0 of y by definition. And you can also compute, now with this solution, note that it's very easy to compute phi dot 0 as I go, so phi dot 0, which is the derivative with respect to x0 of phi, as x0 goes to 0. So phi goes to phi 0, as x0 goes to 0. What about its derivative? I'm going to the boundary, I go to phi 0. How does the derivative behave? So you just compute the derivative of this function with respect to x0, and then you set x0 to 0. And you see that this phi dot is equal to d times this constant, there was a constant, d times a constant times x0 to the d minus 1 from taking derivative times the integral dy phi 0 of y over, and I put x0 to 0, x minus y to the power 2d. Okay, so we see that we have phi 0 at the boundary, and the derivative goes to this type of integral of phi 0. And that's done, that's basically it, because now you can easily see that this integral here that you integrate you can, by Stokes' theorem, relate this to an integral at the boundary of something like phi n dot derivative of phi. Do you agree? It's just d squared by integrating by part is phi d phi. This normal derivative at the boundary is just a derivative in this direction. It is just d dx 0. And so when you go to the boundary, you get phi 0 times the derivative that you just computed. So what's the final result for the action? Is just the integral of phi 0 of x, phi 0 of y, where I integrate over x and y, 1 over x minus y to the power 2d. So that's the value of the action. And so, in the classical approximation, that's the value of my path integral, just this exponential. And so we conclude that this generating function gives me, in that approximation, exponential of that. Right? So take two derivatives of phi 0 to construct this correlation function. What do you get? You take two derivatives of that, you get exactly this factor here. But what's this factor? It's exactly what we wanted to get for a CFT. So we conclude that we get exactly the CFT two-point function with delta equal to d. Then there is a nice exercise that, so what we learn is that I should think of this scalar. For each scalar in the bulk, there is an operator at the boundary. So the operator at the boundary triggers a scalar in the bulk that propagates, starts at some value and propagates and interacts. So that's exactly the usual picture that we draw in holography. We say that I have my boundary, and I triggers a bunch of scalars that propagates, and this propagation is not a cartoon. This is a propagator. What this propagator is this scalar we computed. And then this propagator, in the two-point function case, it just connects to 2 points. But now we could imagine doing interactions, and for example, doing 3 points. And now I'll have one propagator, another propagator, another propagator, and now I'll have this point here. And I will have two final diagrams. I integrate over this point. And I could now have also ball-to-ball propagator, not just boundary to boundary. And now I start doing final diagrams like this. And these are called Witten diagrams, since this paper. And that's a formalism that explains that you should do these diagrams where you have these ball-to-boundary propagators. And if you want to do perturbative computations, those diagrams compute correlation functions of operators. In this case, 3 points in the circle. And different operators at the boundary trigger different operators in the bulk. Operators like scalar operators of dimension d should correspond to a scalar, massless scalar at the boundary, in the bulk. If you did massive scalars, then you would see that the CFT gets changed and you would get this result. When m goes to 0, it becomes d again. How would you arrive at this result? You would repeat exactly what we did adding a mass to the computation. How? This Laplace equation would get an extra m squared term. Because of that extra m squared term, this power here now would not be d, but it would be changed. And you would change this power. Now, because you change this power, you have to change a few powers, and it's no longer true that the solution goes to a constant at infinity. Now, the solution with a mass is not compatible with going to a constant. Instead, you have two modes. One mode grows, one mode decays. And it depends on the value of the mass. and that's what replaces constant and decaying mode. And you say the growing mode, I'll take it to be my phi 0. The way it grows, the prefactor of how it grows is my phi 0. But now it grows. So it is not, now it depends on how I approach the boundary. So now it's not true that phi 0 is just a weight 0 object that I just go to the boundary. Now it's like it contains some power of the matrix, some power, like a wild factor. And so now it's all consistent because now first you do the computation and you get now a different number, you get delta. But that's predictable because we said that this phi 0 now, it's not dimension 0 anymore, now it has dimension. And because it has dimension, this semi-identical coupling, the dimension delta will not be d. It will be d minus whatever that dimension is, so that this is ordinary. And of course it works out. You do the computation and you predict first, just based on the way it goes, what's the dimension of this guy. So you know what the dimension of this should be. But just to be sure, you do the two-point function exercise like we did. You get some nice phi, you take derivative, you get some nice expression, this t changes to the delta, and it all works out. Then you can ask, this was all nice for scalars, and so then you ask, then there is a discussion of, this looks kind of interesting, because you see that if the mass is positive, this is bigger than d. So this is bigger than d, equal to d, or smaller than d, depending on the value of the mass. Like mass 0, mass positive, mass negative. But operators being bigger than d, equal to d, or smaller than d, it's very relevant, it's very important, right? Because these are marginal operators, irrelevant operators, and relevant operators. Right? So it's crucial that we have this freedom of doing these three cases. So this, for example, smaller than d, works if the mass square is negative, which looks a bit weird, but actually you can have negative mass provided it's not too negative in EDS. And so we see that if you want to predict, if you want to study scalar operators that are, for example, very irrelevant, with dimension that's very big, you should study scalars in the ball that are very heavy. And so if you have a bunch of fields in the ball, for example, string theory will contain massless scalars, like the dilutant. It will contain massless spin fields, like the graviton, but it will also contain massive string modes that are very heavy. What happens to these very heavy modes? The mass is huge, the dimension is huge. These are just dual in the CFT to operators with very big spectrum. Very irrelevant operators. So in ideal CFT, we should have this big gap. There should be a bunch of stuff with dimension which is very small. But then there should be a huge gap, and those are the string modes. That's special to CFTs that should have an holographic dual. And there are a bunch of other things that were pointed out in this paper. For example, it was pointed out that the scalar will, as you go to the boundary, in this case it approaches a constant. In this case it explodes, and in this case it goes to 0. So in this case you have two decaying solutions. In this case one constant, one decaying. And in this case one exploding, one decaying. Now, if this explodes, it's problematic. Why it's problematic? Because it's problematic to use a linearized approximation. Because if something is exploding and you are treating it as a small perturbation, you have to be careful, because as you go to the boundary, it's very big. So you might lose control of what you are doing close to the boundary. So that means that sometimes you have to think of this formally. You have to think of this as these fields being infinitesimal, just as a generating function. And that's exactly what we do in CFT. In CFT, we can compute correlation functions of irrelevant operators. That's totally fine. I can compute correlation function of f to the 8 at a bunch of points. No one stops me. But it's very hard to define exponential of integral of f to the 8 with a finite coefficient. Because if that's irrelevant, it will trigger a lots of other terms. It's not just well defined. In the UV, it's very complicated, right? It doesn't have a good UV limit. And that's the analog of this phenomena here. Whereas when it's relevant, you can make sense of this object even in the exponent. He also discusses, well, so we learned that the theory must have various scalars in the ball corresponding to various scalars that you have in the boundary. Scalars with different dimensions should be scalars in the ball with different dimensions, with different masses. But you have other things. Not everything is a scalar. You have objects with spin. You have objects that are vectors, not scalars. You have objects that are spin too, and not scalars. And so, for example, you could imagine this A, for example, this field would be replaced by a gauge field, A mu. Then this would have to couple to a current, J mu. A conserved current, because this is gauge invariant. For this to make sense, this needs to be conserved. And so, if you have a gauge field in the ball, you must have a theory that has a conserved current in the boundary. And so, correlation functions of those currents will be computed by turning on the chromodynamic or the gauge fields in the ball. You turn on gauge fields in the ball, and you say, now I do my path integral over gravity where my Maxwell field is turned on. And it needs to approach different values at infinity. And by approaching the values at infinity, then I compute this partition function in gravity with the Maxwell field approaching some values. And then I take derivative with respect to the Maxwell field to compute correlation functions of currents in my CFT. Conserved currents. There are other objects in the CFT. For example, we have T mu nu, which is a spin 2 of a very important stress tensor, which is a bit like a current. It's also conserved, but it's spin 2. So it should couple to something that is spin 2, and that something is the metric. So fluctuations of the metric are precisely what couple to the stress tensor in CFT. And the fact that this fluctuation have diffeomorphism redundancy translates into the statement that the stress tensor is conserved. And so correlation functions now that involve at the same time scalars, stress tensors and currents correspond in supergravity to saying that a bunch of fields have non-trivial expectation values, and maybe some scalars go to some phi zeros, the gauge fields go to some a zeros, the metric goes to asymptotic metric plus beta 0, and everything is turned on. All the fields go to non-trivial values. Of course, in practice, often those values are infinitesimal. So you do perturbation theory around trivial values, and you just draw a bunch of propagators. But these propagators now will have spin sometimes if you do spinning some. And then you do Simon diagrams where you have these propagators, but not only scalar propagators, but you could have Gluon propagators as well. That will propagate from points to boundary. And then this will compute a correlation function where now I have some current as well, for example, in this case. And that's how the setup of this duality goes. Yeah, this was way less than what I thought I would cover. So I said we were going to discuss three things. One, a prescription for how to compute correlation functions that leads to this proposal that says that Witten diagrams compute correlation functions. And I said we're going to do two other things, but we are not. The two other things was, how do I interpret, what's the dual, what should I do in, this is in gravity, this is in the CFT. And the idea would be, how should I do, for example, what should I compute in gravity to get the spectrum of the CFT? And how should I think about the fact that in gravity I integrate over metrics? So it's not a space-time, there is I integrate over space-time. So how does it make sense to say that I have one space-time if I should integrate over space-time? I mean, this you can read in the paper what's the answer to this thing. But the point to emphasize is that what Witten is doing here is trying to understand very generally how these dualities should work. It's not about n equals 4 and ADS 5. It's about if you have a theory which has a boundary, and if there is some theory at the boundary and some theory at the pole, how could the two ever be related? And one option is you have fields that are in the pole, but they approach boundary values. The boundary values work as sources for the boundary, and so it's giving us a plausible way that should be the generic way, the general way of thinking about all such duality. And if you do ADS 5 times S5, this small d is 4. If you do ADS 4 times CP3, this d is 3, and so on. But otherwise, the formalism is very general, and this proposal that the correlation function should be given by path integral is very general as well. Okay, so I think that's it. So we can finish this could be the last lecture. I don't think we need to have presentations about this paper. So I think that's it. So in next year, we can, or in December, we can run it again. If you guys are around, but I think these were 5 good papers. We started with gravity, we ended with gravity again, with differential equations. Yeah. Lots of statistical mechanics in the middle. So I hope you enjoyed. And that's it. Questions about this paper or did you try reading the paper? You have questions? I mean,
Well, in which, because I mean, I know people try to do like this kind of duality for the space-time. Is there an easy way to see in this example, for instance, where would it be problematic to try to define this massive scalar D in this and try to argue like for do this kind of argument for sources in the boundary, etc.
Yeah. So a problem is related to this issue of times and where are the times and so on. So here, the boundary of this space-time. You have a nice boundary. So here we are doing Euclidean, and it's really a ball, and the ball has some surface, so it's more like a sphere. In the ADS case, your boundary has one time and space, and things are nicely causally connected. That if I put stuff at the boundary, it influences the ball, and so on. Now, in the theater, the boundary is at time equal to plus infinity, right? It's at the end of time, right? It's not, so it's conceptually it looks very different. It is not putting things in a box. It's waiting till the end of the universe and seeing how things are. So the theater looks more like you're doing a path integral to compute a final wave function. So from that point of view, it smells different. On the other hand, the zither and anti-zither and spheres, they're all the same thing up to a few signs. So some people think it shouldn't be that hard. Mathematically, it looks very similar. So who is right? Is it true that mathematically it's very similar and therefore the zither should be a small adaptation of all this? Or on the other hand, the fact that it's really at the end of time that we have what we would call the boundary, and that the boundary is a time light instead of space light, or the other way around, I don't know, but it's like this instead of like this. The fact that the boundary is very of a different nature from the signature point of view, does it make a big difference conceptually? Well, I don't know what the answer to that is. I would say that I think very few people, in my impression, is that few people explored trying to take n equals 4 and analytically continue n equals 4 to try to see if the analytic continuation could look like some kind of a de Sitter theory. Because I think this analytic continuation requires going to complex finite coupling, and very few people control finite coupling. You need to know this quantum spectral curve, integrability, and so on to go to the complex plane. And people that like to speculate about de Sitter are not people that like to do computations. So, so I think there is a window of opportunity there. I think it should be explored a bit. What does it mean to take n equals 4? analytically continue decoupling in ways that you would try to do it if you were to try to flip a few signs to go from ADS to the system. And see, some things become non-unitary, but does everything break down, or is the kind of non-unitarity that you get what you would expect for a wave function of cosmology? Maybe it's not so bad. But there are attempts. There are attempts of doing DSCFT. If you Google DSCFT, or if you put on ChatGPT, you will find many examples.
Just a second question. In this paper, within basically postulates that the relationship between the partition function and the classical action, then he goes on to give like a bunch of those examples in comparison to experiments and that kind of stuff. So, but he never gives like a formal a formal proof of this equality. Do you know the state of the art of that kind of stuff? How close are we to actually producing like a mathematical proof? There, like a proof for a low dimension, that low dimensional CFTs and EDS bases. Do you know how work in this direction?
Yeah, so I mean, it depends. So if you ask, find the dual of some gravity without supersymmetry, it's we don't know. For the particular n equals 4 example, clearly it's true, because I mean, there are so many checks, there's no doubt that it's true. Right? I mean, this duality is something very wild, that you have this holographic duality in one more dimension is given to less dimensions. How could this ever work? The fact that you start checking things and things don't immediately fail, it's like a miracle, and it's super non-trivial. And it's very precise, right? You say this theory is equal to this other theory, and you can now compute dimensions on both sides and see if it matches. And also it's important to say that sometimes, because of this low energy limit that I mentioned in the beginning, you can follow what this quantity would be before you took the low energy limit. You could ask, I compute correlation functions. What are correlation functions? Like a scattering experiment. I have my table and I put a bunch of sources at a bunch of points and I see how the table reacts. And I can set it up in string theory and then take the low energy limit. And then see what I would land on, and you would land on this. So you could argue from this, starting from string theory, for example. You can, there are other dualities, or watch the Wilson loop that we discussed in the CFTP. And you can, on the one hand, you can try to guess. You can try to say, oh, a Wilson loop is a lying object, and string theory contains open strings, so maybe the open strings need to end on that content. You can guess the only natural thing you could, and you would be right. But you can also deny it. You can say the Wilson loop, I can think of it as a very heavy particle. How do I engineer a very heavy particle with a bunch of d branes? I separate one of the branes a lot, so that the string that stretches between the two is very stretched, so it's very heavy. Then I carry it around, and that defines a Wilson loop. Now let's take a low energy limit of this picture. See whatever you get, you get. And then you will see that you will end up on the prescription for computing Wilson loops. So it's often the case that but this low energy limit is a bit hand waving as well, because it has some regime of validity and so on. So in ADS-CFT you always have many incomplete proofs, many evidences that things are correct, but you never have theorems. I mean, but that's okay. I mean, in the replica tricks that we were discussing, also, I mean, it was hand waving a lot. In the end, you check if it works. I think. Yeah, having proofs, I would say, it's overrated. It's about proofs.
I guess the better question to ask then is, should this duality be expressed? Would there be a different way to express this duality? Because it seems to me that the way he argues in this paper, that he kind of pulls it out of the head. You know, what should be the most natural way, which is this comparison of the this coupling of the fields to the CFT operators, and then you put this equal to the supergravity partition function. Why couldn't you, for example, you conjecture this duality being like a straight up match of the correlation functions on the bulk on the boundary. Why could you do that for instance?
You could. You could. I mean, another equation I can write is that this is equal to correlation function of vertex operators in string theory. If this operator is a single trace operator equal to a string, this is the true equality zone. This looks more like what we want. Correlation function in IFT or correlation function in string theory. Now this is when I have a bunch of vertex operators. What do vertex operators do? They tell me to insert strings at a bunch of points. In other words, what do? They impose the boundary conditions for my string close to those points. But what is that? That's the same as putting a stars. So then, in the supergravity limit, you can show this is the same. But if you go beyond supergravity, this is more precise. If you are dealing with operators that are dual to string modes, for example. And that is what you would see from the derivation of low energy. Because you would say at low energy, I have some string that interacts with the stack of d-branes, and therefore it's a string, so it's a vertex operator. I stop. On the other hand, it interacts with the stack of d-branes, so it hits the stack of d-branes and it produces some disturbance. That's a local operator on the brain. That's what I've done say. And then you draw some large N diagrams to see, oh, indeed, I'm putting an operator, it's like putting a hole in the final diagram, you handle it a little bit. So this is a natural definition. And then vertex operator imposes boundary condition because that's what they do, and that leads you to this prescription.
So in other words, this natural prescription is, as far as we know, the most general prescription. They could possibly do between like a field theory and a theory on the boundary. Would you call it that?
Yeah. I prefer to think of so there are two natural boundaries for ADS. One is this sphere. I think of ADS as this Lobachevsky disk, of this disk of the like Escher disk with the fishes and so on. Then it's like ADS is like a sphere. There is another way of thinking of ADS. It's like going to the boundary in a slightly different way, where ADS is more like a cylinder. I have a cylinder, and ADS is like a cylinder. And then my boundary is the boundary of the cylinder. The boundary of the cylinder is a sphere times time. So I like that way of thinking more, because now both space-times, they share going up. One you go up inside, one you go up outside, but it's the same generator. Then the duality is just a statement that I have an Hamiltonian that moves me in time. That Hamiltonian is H, and I can put an index bulk to say it's the Hamiltonian that evolves whatever happens in the bulk. Or I could go to the boundary and I would put an index boundary, and I would say I have states in the boundary and they just evolve. And ADS-FT will be the statement that they are the same, that H bulk is H boundary. So that's like the Hamiltonian version of this path integral version. And the two are the same, because in a CFT, doing things on flat space, or on a sphere, or doing things in a cylinder are related by Weyl transformation, so in practice you can think in both ways. But that way I think it's more elegant. I just have a space which is a cylinder, and I have a time evolution that evolves things. And the duality is the statement that I can either prepare a Hilbert space in the bulk and evolve it, or prepare a Hilbert space in the boundary and evolve it. And they should be the same. And that's the last thing I was going to explain. That's the last section of the paper. That's the Hamiltonian formulation. That implies this one, but I find it more transparent. Cool. Okay.
Thank you.